Everyone. I have to apologize first because I may not be able to answer any of your questions.
That'll save time.
Yes, but what Frank wants to present here is his or our latest results that is impressed in Nature. So you don't need to wait too long before you see this. Yeah, so it's about the detection of complex organics from Enceladus. And so we have this slide showing that this is Saturn viewed from the other side. I mean, Sun is somewhere there, so you see the forward scattering light that actually highlights this bluish diffuse thing that is we call E-ring. And I put the Earth here, not because it's here, but just for scale, that you know it's a gigantic feature, and all of these materials are fine micron-sized icy grains that emit from this satellite we know, Enceladus. And so you can see that the nice thing about images, it basically tells you the story that grains emitted from Enceladus, because it's so tiny, they are launched with speed high enough to escape its gravitational well and therefore enter the orbits of Saturn, forming this diffuse ring. And the nice thing about this is that for the measurements we're going to make with the cosmic dust analyzer on board Cassini, is that it's an in situ type instrument. That means it measures materials where the spacecraft goes. And so if you cannot go there, you basically cannot measure. And what it does here is that basically it puts the material, tiny pieces of Enceladus subsurface ocean into the orbits, and where spacecraft have a lot of time to explore and measure, collect, and accumulate data, and we can start to look into things, not just the most obvious things, like these are water ice, but more detailed information. And the method we are using is based on the mechanism called impact ionization. That's when you have encounter particles that hit the detector with a speed of several kilometers per second. It's very high. And among the fragmentation of that particle, it also produces some amount of plasma. And by setting up an electric field to separate this plasma, we got a linear time-of-flight mass spectrometer, so we can know the elementary composition of the incoming particle. And the first thing CDA sees in Saturn is water, which makes perfect sense because, as Bill laid out, that Saturn is an ice-rich system, and we have suspect E-ring is made of water. And here shows the clusters of water cations. So we have a relatively moderate mass resolution, but you can still tell the water clusters. And the other subpopulations, after a while, Frank realizes that there's a population rich in sodium. So that because the sodium is very easy to ionize, even just 1 of 1,000% of the 1 of the 1,000 of sodium compared to water will alter the impact ionization spectra dramatically. And that is, as Kevin mentioned in the first day, a solid proof that this is a tiny, quick frozen droplet of subsurface water of Enceladus. And what Frank's pushing further is that beyond this, most of E-ring grain we saw is pure water ice. And there's a subpopulation, about 10% of the spectra we analyzed are salty water. And there's a big fraction of them are actually containing a little bit of organic. But what this talk will talk about is even a subfraction of these that contains as much as about 1% by mass of the organics. And the spectra look like this. So this is time of flight. Basically, the time goes with the square root of mass, and this is the amplitude. So these are the cations detected by CDA. So there are several features, as Frank marked. First, these are the water clusters, as you show in the pure water ice. And as you can see, that a lot of mass lines are not associated with water, means that organics actually plays a good part of this. And also the easily ionized sodium. And even though the lines seem significant, but because they are easy to ionize. And secondly, the dominant feature he wants to point out is these aromatic rings with a 6 and 7 carbon here, and also these what is that? This series of unsaturated breakups of carbon species from C3 to C7. And from lab experiments, we can shoot organic particles onto the detector, and this kind of pattern has been registered, and therefore these are most likely originated from these aromatic rings. But in addition to this, there are a lot of what he calls high mass organic cation series that range from Ca to C15, and most likely even beyond the detection range of CDA. That's what this arrow means. And if we can do some statistics based on the, I think here only 64 of spectra, so the number is really tiny, but the detection is significant, that you can see that the intervals between these high mass organic cations is about, the average interval is about 12.5. That is roughly indicating they are unsaturated bounds, structures in between here, and indicating they are larger fragments that probably causing all these, and also the aromatic structure. And so there's additional information that he squeezed out from the CDA data, is that there's in addition to the typical range, roughly ends at 200 U, there's a reduced recording of, the extended recording with reduced frequency, that means reduced mass resolution for the spectral mode. And you actually see that this is one spectra, and these are the water lines and the high mass organic cations you see here. And there are actually structures outside of the detection or regular detection range, and that's up to about 2000 U. And if we do a line count for out of 83 spectra, and there are actually a good fraction of them actually have these mass lines, which we can definitely now resolve around 800 and 1600 U. So it's also likely indicating that these actually, we don't really see the paramoleculars. So this is the first summary about the interpretation of spectra, that we see a significant subpopulation containing these high organic cations that most likely coming from molecules that is outside of the mass range CDA is capable of. And I don't think I want to read through this, but what else should I tell? Oh, okay. So something I didn't show you, or he didn't ask me to show you, but just show in writing that he also identified oxygen-bearing and nitrogen-bearing species from the spectra, which might take some more knowledge I don't have to show you. But the conclusion here is that the interpretation from all these spectra collected with high mass organic cations are that these likely to be macromoleculars with organic that have containing oxygen and nitrogen bearing functioning groups, and aromatic rings at 6 and 7, and they are connected by aliphatic chains. So next, so this is from the subgroup of spectra we have, and now we are going to explain into, or kind of adapt this to the pictures Frank has to explain how these grains are formed. So from the soil-rich particles, there's a concept that water bursting from at the water vacuum interface that actually produce these droplets that quick freeze to preserve a salty water sample, and as it ascends to the vents, it accumulates some more water ice vapor onto it and get ejected away from Enceladus. And so this is a concept that grains could form from the water, or tiny as water droplets, or they could form from pure condensation as a nozzle effect of these sublimating or vaporized water vapor getting away from the subsurface water reservoir. And how do you form organics in such concentration? That may not mean that the water is actually contained on average, say, of 1% or around that of organic, but it's likely that organics are kind of accumulate at the surface of the water vacuum interface, and these burps, bubble mechanism also, by doing that, it also release, instead of water, but tiny bits of organics, and then it start to accumulate just as salt-rich water droplets. They accumulate water as it's going up from the water surface, and therefore forming these organic rich or relative rich particles. And there are some implications is that that first, these organics, high mass organics grains is actually from salt poor grains, so they are not really mixed well with water, and that's easy to understand because these at these complexity they do not dissolve, and so they also will not form in the gas phase because they are just so complex. And so 2 minutes, okay. So that's the hypothesis that this is the water organic film on the surface that bubble bursts producing these kind of particles, and you ice coat it along the as it travels through the vents. So this is another picture, basically blown up, and and another figures I believe half of you will be more familiar than I do is that we start to think about this. He told me about this idea, and then we found this paper that describing actually on Earth similar process happening. That's a organic film on the surface of the ocean, and by similar process, what he imagined or speculated, and you actually produce organic grains and or aerosols into the air. And the interesting part is that the pure organic part is actually consistent with the amount of organic we see in the CDA spectra. And so this is probably the last slide. And combining with the Choblet paper, that what he wanted to argue is that these complex organics may likely to be forming from the hydrothermal reaction deep in the core of Enceladus, and by the mechanism provided by the modeling work of Choblet et al., they actually transported to the south polar region with relatively confined, rotationally confined plume source, and therefore be able to accumulate over there and responsible for these high mass organic molecular ice grains we see. And this is the answer to all of your questions. And that's all. Thank you.
Thank you very much. Guess you're not in. Are you answering questions?
I can try.
You can try one while we transition. So where's
yes.
Nick?
You already know this, but for the general audience, the INMS also saw plenty of evidence for organics and higher molecular history. We're not able to definitively identify what they were. So I think this all fits together.
Yes, yes. I think it's likely that these. I mean, they also see indication of ice grain impact into their chamber, and this might be what it's all about. That from the solid phase.